Good morning, everyone. My name is Adam Marcus. I'm an associate professor at California College of the Arts in San Francisco, and I'm also a member of the Acadia's board of directors. We're here to kick off the morning with the first of today's 2017 Acadia Awards, the Acadia Innovative Research Award. This award recognizes innovative research that contributes to the field of digital design and architecture, particularly work that has the potential to transform contemporary practice. Previous recipients of this award include Andy Payne, Skylar Tibbetts, Martin Bechtold, Elena Manfredini, David Rutten, Branko Kolarevic, and Mark Burry. Today, it's my great pleasure to introduce this year's recipient of the Innovative Research Award of Excellence, Wes Mcgee. Wes is no stranger to this community. He has exhibited and presented at many Acadia conferences. I think the latest count on CumanCAD is 7 or 8 papers. His work at the University of Michigan Taubman College of Architecture and Urban Planning, where he is an assistant professor and director of the Fab Lab, is notable for both its range across multiple media, techniques, and processes, as well as its depth. Wes's work focuses on the interrogation of the means and methods of material production in the digital era through research focused on developing new connections between design, engineering, materials, and manufacturing processes as they relate to the built environment, with the goal of seamlessly integrating critical feedback between fabrication constraints and design intent. The work spans multiple realms, including algorithmic design, computational modeling of material behaviors, industrial control technologies, and the development of novel production processes which utilize industrial robots as bespoke machines of architectural production. As a founding partner with Brandon Clifford of the studio Matter Design, his work spans a broad range of scales and materials, always dedicated to reimagining the role of the designer in the digital era. In 2013, Matter Design was awarded the Architectural League Prize for Young Architects and Designers. In 2014, Wes was the co-chair of the Robots in Architecture Conference in Michigan, and recently, last year, co-chair of 2016 Acadia Taubman College. I would add also that one of the most remarkable things I think about Wes's research and his practice is its highly collaborative nature, which has only magnified his impact on this discipline in this community. So please join me in congratulating Wes on the 2017 Innovative Research Award and welcoming him to present his work.
Thanks, Adam, for the great introduction, and good morning, everyone. I want to start out by thanking and congratulating the 2017 chairs on what's really been an incredible conference so far. And I especially want to thank the awards committee and the Acadia community at large for this award. It's truly humbling to receive it, and I'm doing so on behalf of a long list of collaborators, mentors, colleagues, students, and friends. I was especially excited by this year's conference theme, as I think it provides an opportunity to think about the discipline, and more specifically, what interdisciplinary collaboration means in the fast-paced research context that we all live in. The projects I try to work on span multiple realms. Often we develop a trajectory in an academic context, collaborating with a diverse group of experts, or increasingly working to develop longer-term collaborations with a variety of industrial partners. But the most successful of these collaborations are not focused on simply transferring resources or the sponsorship of a specific project, but instead explore new approaches in the transfer of new knowledge and new ideas between parties. And I want to continually highlight collaboration throughout this presentation, as from my perspective, it's the single most important ingredient in innovative research. I also want to highlight some of the failures that have happened along the way, if for no other reason than to question our understanding of failure in this context. From a disciplinary standpoint, I think design and engineering often have a different definition of failure. To oversimplify, architectural experiments at the pavilion scale often ask, does it stand up? And engineering is often concerned with the degree or the cause of the failure. A core component in our work, which is intrinsically related to failure, is testing. As the techniques we explore have become more complex, we've also had to expand our methodology for testing. Yesterday, I particularly enjoyed when Neri showed the current research exploring the design space of the 3D glass printing. I think this type of rigorous parameter space exploration is a critical step in developing innovative material processes at full scale. For us, the productive shift has been the inclusion of real-time measurement, control frameworks in our development workflows. This allows us to measure responses to inputs along with material behaviors. The ability to synchronize complex image or spatial data with real-time process information is the first step to beginning to develop processes which can adapt to changing conditions. And you probably briefly saw this image in Sean's presentation yesterday, but for us it was a big step to be able to synchronize image capture with very specific pressure ratings so we could compare the position of these actuators across different changes in the knit structure. And so one area of research that I've been consistently focused on probably for the last 10 years, as Adam mentioned, has been the interrogation of design to fabrication workflows. It's been discussed extensively in the Acadia community over the last few years, but I think there are still challenges to be solved. And I wanted to go back in time for a moment to a project which is now 10 years old and resulted from a collaborative research project and course at the GSD that I co-taught alongside Martin Bechtold and Monica Ponce de Leon. We had just installed the robots at the GSD and were exploring the capabilities of an abrasive water jet cutter mounted on an industrial robot. We're not only concerned with cutting complex joints and understanding the overall accuracy of the system, but we were also exploring erosion methods, which required relatively high feed rates and to slow the rate of material removal. The process was highly difficult to control. It resulted in a dramatic variation from what was designed and what was produced. But the promise of variable thickness erosion in stone is still an exciting territory. More interesting from my perspective of that project today, though, was that it highlighted a massive disconnect between our capabilities as computational designers and our ability to translate these designs into machine instructions to control these new tools and processes. And this disconnect provided a basis for some of the challenges that I'm still working on today, specifically how to make fabrication processes more intelligent and accessible, as well as to expand these workflows to support new processes. Especially interesting are emerging ways in which real-time sensor feedback can influence not only the process of materialization, but also the generative design process itself. I think in many ways the growing interest surrounding industrial robots within architecture has provided an ideal platform to continue this work. Robotic tools, inherently generic, require an integrated approach which considers this entire process from design to production. So we took this requirement as a prompt to explore as wide an array of processes as possible. One of our earliest explorations was a shift away from the idea of robot as simply motion control for a tool. This wire bending process positions the robot as one component in a larger automated production chain, where instead of fully designing tool paths, the system is fed a sequential recipe of components to produce. The earliest projects, often based in collaborative design studios and seminars, relied on manual assembly of the parts, exploring how a simple standardized material like 1/4 inch or 3/8 steel rod could be amplified into something much more spatial. Eventually our robot cloned itself, and that's allowed us to explore positioning and automated assembly, as well as incorporating sensing for part localization. Ultimately, this research produced an infrastructure which enabled several larger installations, as well as numerous collaborative studios and workshops, and it's really become a tool that's frequently used by students working on a thesis independently. And our experience in developing that rod bending system led to a number of other projects, in this case a parametric glass forming kiln, where we are working to build entirely new machines. These systems rely on industrial control frameworks, and while the learning curve was challenging at first, it's both expanded and accelerated the pace at which we can develop new processes. And this intersection between machine control and an increasingly expansive design space is really where my work lies today. And so far, I was mainly introducing projects that occurred in an academic research context, but I also want to highlight the ways this intersect with my design practice. As Adam mentioned, Matter Design is an interdisciplinary practice founded in 2008 by myself and Brandon Clifford. Brandon's faculty at MIT, but unfortunately he's in Rome right now. So Brandon and I come from different disciplinary backgrounds. He's trained as an architect, and I studied mechanical engineering and industrial design. The work spans a range of scales, from product to architecture, but the projects all share the theme that the methods of making are intrinsic to the design process. These projects also share the theme of wanting to push back against typical industrialized sheet materials, which, especially in 2008, we felt were dominating the discourse of fabrication. The first project, which I always kind of look back to as a very pivotal one for us in the practice, was a competition in 2010 to explore the robotic hot wire cutting process to produce a 50-foot tower of foam. Of course, that wasn't what the brief of the competition asked for. It just asked for something digitally fabricated that could fill up a 10 by 10 space. But what they didn't say was how tall it could be. We wanted something that would be an icon for the event. The form in this case was rhetorical. So what looks like a tensile surface is actually a post-tension stack of polystyrene foam. And it's hollow, so there's a double wall poché. We were very interested in exploring the kind of topological freedom that wire cutting so easily does, and which you've seen in so many projects since then. But it also began a project of exploring methods which privilege volume and more recently mass. So a critical theme in our work is the application of simulation and computational tools which model material behaviors or structural performance. We attempt to embed these at an early point in the design process, along with an understanding of fabrication constraints which become integral to the development of the overall system. These computational tools are often intended to subvert a purely optimal solution in favor of secondary performance criteria. On the left is a design for a thin shell compression vault solved by the typical particle spring form finding approach. And on the right is a proposal for a system that responds to form as an input by varying its thickness to maintain the compression-only solution. If I remember correctly, this was actually done in Axel Killian's studio when Brandon was a student at Princeton. These alternative yet still viable solutions are what interest us most. So we developed a project called Le Voûte de la Fève, which was installed at the Knowlton School of Architecture Gallery. The most interesting application in my view for computational design are systems which require this negotiation of multiple performance criteria. In this case, the assumption is that the basic design of the global form is fixed, possibly driven by program, acoustics, or some other input. The system then responds by opening or closing the apertures to manipulate the volume and therefore the mass of the individual units. Like many computationally derived forms, the resultant aggregation required a high population of unique components. But this project in particular propelled our interest in developing software tools which enable feedback between fabrication constraints and the design environment early in the process, as well as attempting to simplify this process of programming complex toolpaths. In this case, we were also using wood as an immaterial replacement for something more substantial. The project also provided a test bed for exploring aggregation of increasingly complex forms in 3D. So based on our experience with the Vault project, we developed a design for a small installation here at MIT's Keller Gallery called the Round Room. And so many of the projects we do at Matter Design look at historical references as a source for innovation. In this case, we were looking at the Incan masonry of Peru. These stones have effectively zero-tolerance joints, and some of them are literally larger than cars. So the challenge was, how do we adapt this process how do we adapt these Incan techniques of scribing and templating to a prefabricated process with relatively unknown tolerances? Around this time, we'd begun talking with a commercial fabricator, Cora Stone, who many of you may be familiar with. This was approximately the time when they were awarded the contract to fabricate the Collier Memorial here at MIT. And this project seemed like an ideal test for new workflows in their process. Cora Stone had extensive experience with stone machining, but they had rarely had the opportunity to work with computationally derived geometry. And so for us, it was also a unique opportunity to act both as designer and consultant, working with their teams to develop new machining strategies and approaches. It was also effectively the first project where we didn't fabricate the entire thing ourselves, which I have to say is a pleasant change over some of the early projects. The partnership with Cora Stone was incredibly valuable, and it's now resulted in a 3-year fellowship being established where each year summer. One MIT and one University of Michigan student were on site for the entire summer at their facility in Madison, Wisconsin, to research digital workflows in stone fabrication. I think this type of collaboration between industry, practice, and academia is critical to test new approaches outside of the typical research lab setting. Fellowship also led to finally being able to test these techniques in stone. And in the second year, we produced a project called Caldarium. Caldarium resulted from possibly the largest and most interdisciplinary team of all the work we have been involved in. Aside from Brandon and myself, we also worked closely with Caitlin Mueller from MIT, who many of you will know, as well as fellows Inez Ariza and Shan Sutherland, and the team at Quora. And it continued our ongoing interest in the question of how to build a complex shell with little or no scaffolding. And the project specifically looked at two types of historic details in stone assembly. The first is the act of carving a connection, which is subsequently cast using a low-temp metal alloying. And the second is a more procedural act. In the case of ink and stone work, is closely associated with the sequence of assembly. The research revolved around a computational methodology developed by Inez, which incorporates a dynamic simulation of the assembly of the structure. So most form-finding research you're familiar with focuses on equilibrium of the final form, assuming that extensive scaffolding and sintering will deal with the intermediate states of construction. The second exploration in the project was the usage of an in situ cast tension connection between individual elements of the structure. These were also tested to failure to inform the overall development of the joint. So the ideal joint would fail in a ductile manner before fracturing the stone. From these tests, the team was able to develop a parametric joint which could adapt to varying load conditions, as well as the sequence of assembly, requirements of temporary support, and the subsequent casting process. These tension elements ensure that equilibrium is maintained throughout the assembly process. But again, I want to stress that this type of exploratory research is really only possible with the support of an interdisciplinary team, especially one focused on experimenting at full scale. And I see this as a critical step in closing the gap between industry and academic research. So the final project I wanted to share is called Cannibalistic Architecture, completed this past August at the Seoul Biennale, again in collaboration with Quora Stone. And so one aspect I think we enjoy at Matter Design about participating in an event like the Biennale is it provides us a chance to respond to a new context. In this case, the project is set against the context of the monumental volume of construction waste produced today. The numbers are truly staggering. According to EPA estimates in 2014, 534 million tons of construction debris generated per year in the United States. It's actually twice as much as the amount of conventional trash that we generate. 70% of that construction debris is concrete, and the majority of it is sourced from bridges and roads. And so to put that number in perspective, that's 1.15 tons of concrete being landfilled for each US person every year. So against that background, the project asked, can we efficiently reuse volumetric construction waste? Or to put it another way, can our cities digest themselves? And so as a precedent, we again looked at ink and masonry techniques, and we combined these with contemporary methods of scanning and cataloging the available rubble and quarry stone remnants. We found a demolition contractor in Madison, Wisconsin, who could find us large blocks of material in various sizes. And we also had access to Quora Stone Yard, which makes for some pretty interesting moments in the wall where we cannibalized parts from other projects they had worked on in the past without asking permission from the owners. Machining concrete is not a commonly used fabrication process, especially reinforced concrete. To put it in perspective, effectively, you can machine through rebar with the typical stone tooling, but you have to effectively set the feed rates for the rebar, so you're going to slow down your production process massively. Not to mention you're constantly changing the hardness of the material. And I want to stress that reuse is really only one of the many potential approaches to address these waste stream issues. Obviously, more efficient use of materials and additive processes are quite interesting to us as well. And as with many aspects of our research, it was also an opportunity to challenge the design to production workflow. It would have been much easier for Cora to work with a natural stone, sawing slabs and machining parts like they do every day. Ultimately, the project continues our fascination with the heavy, pushing back against processes which attempt to pack material into thinner, flatter mediums. It also attempts to mine material expertise as a way of exploring forgotten approaches to construction. So I wanted to kind of wrap up now. In conclusion, I hope that some of this work sparks new ideas or questions and promotes a continued conversation surrounding design to production workflows and new materialization processes. As new means and methods of construction continue to advance, I think it's critical that designers and architects continue to explore and disrupt the disciplinary understandings of the design and construction industries. And as a final thought, I want to suggest that collaboration equals innovation. I think this has been critical to my work. And I also wanted to, again, thank all the people who've contributed to these projects. And so as kind of a quick metric of this collaboration, this is a list of the 39 co-authors I've worked with over the last 7 years on some 45 publications and a roughly equal number of exhibitions. Really, none of this work would have been possible without all of their ideas and support, and as well as the Acadia community at large. So thank you.